Hello everyone, welcome to the lecture on filter design. This is Dr. Anirban Dasgupta and let's get started. So far in these filter structures, we have seen how we can implement the filters, specifically the FIR filters and the IIR filters. And what are we implementing? So in the FIR filter, we are given the hz, or in short a polynomial in h of z, and we are implementing the filter structures as per our requirement. And often what is our h of z? This is basically a polynomial in z, or if you take the inverse, which is h of n, which is called the impulse response, this is nothing but h0, h1 and up to some hn. Okay. So now the question is that what are these hn? Of course, you will say impulse response, but how do we get this? And directly the problem of filtering is that we have our h of n, we give the input, we get the output. But the inverse problem or the design problem is that how do we get these values of h such that I get my desired response? Like if I want to make a low pass filter, can I arbitrarily put any value of h? No. So design is that problem where you have to get your filter values correct. So the filter design problem is estimating your h of n giving the filter specifications. And what are the filter specification? So when I say filter, I would say that I need to keep this range of frequencies and remove the other range of frequencies. For example, if I want to design a low pass filter, I want to design the filter in such a manner that it should retain all the frequencies from the range 0 to fc hertz, and beyond fc hertz it should discard all the frequencies. If it is a high pass filter, I should say that design it such that it should retain everything beyond fc, and below fc it should discard everything. Similarly, there can be a band pass filter. So this is low pass, this is high pass, this is a band pass, and these are basically very trivial things. So I am just giving you a hint. So f1 and f2 are two cutoff frequencies for this, and similarly we can have a band reject filter which will reject a specific band of frequency. Band reject or band stop filter, fine. So the problem is that we should give these values, whether what is the type of the filter and what are the cutoff frequencies. Like for low pass and high pass, we should have one cutoff frequency, and for band pass and band reject, we should have two cutoff frequencies. But these filters are typically ideal filters, and in real world we will not get to design ideal filters. So for practical filters, our response will not be exactly like this. Let me change the color. So in real world, our response, I think I have explained this, but still I will get some kind of this. So this is called ripple. So this is pass band ripple, there is stop band ripple, and then there is this transition band. So all these specifications when you give, I have to design my values or design my filter in such a way to get the values of h of n, which gives me a response which is closer to my desired response. And in desired response, I should have some cutoff frequency, some transition band, some pass band ripples, from stop band ripples. And often the type of filter, whether it is IIR or FIR, and if it is FIR, specifically maybe the minimum order filter we need to design. Like with minimum number of coefficients, what is the best response I can get. So typically this filter characteristics are designed in the frequency domain, as I said, and this is in terms of the magnitude response. Like I can give you the magnitude response of the filter or the phase response of the filter, and you have to get the h of n. Now, you may feel that okay, that is pretty simple, because when I know the magnitude and phase response, I know my h of omega, right. And then if I take the I dt f t, then I can get my h of n, right. But sometimes it is not so straightforward, because since this is a continuous time function, it is not very easy or straightforward to directly do the integration and get these specific values of h of n, mainly when h of omega is, if it is not a very well defined analytical function. Again, if you need linear phase characteristics, like my phase should vary with frequency linearly, then you have to design FIR filters. You cannot design an IIR filter. Also, IIR filter have lower side lobes in the stop band than an FIR filter with the same number of parameters. And IIR filter implementation also involves fewer parameters, and they require less memory and has lower computational complexity compared to FIR filter for the same specification. And this is the reason that if this phase linearity is not a mandatory criteria, that you are okay with some phase distortion, then always IIR filter design is preferred. But if phase is a very vital characteristics in your design, then you should go for FIR filters. And if your FIR filters are linear phase, then the coefficients will be symmetric in nature. So, filter design, as I said, can be an FIR filter or it can be IIR filter, and you have to select at the first step. That is the first step of your design, that select whether I want to decide a FIR filter or an IIR filter. So, in FIR filter there are several methods like windowing, equiripple and least squares. There are other methods also like constraint least square, but these are the three main popular, or I would say basic methods. In IIR, the methods involve approximation of derivatives, then impulse invariance and bilinear transforms. So, let us try to understand what are these methods. So, I will give you basics of each method. I will not go into really great detail of this, but you should have a good idea that what are these methods and how to design it if you are given the specifications. So, we will start with an ideal filter, and in ideal filter this is our desired response, which I said that it should have a gain of 1 in the pass band, that is f mod f less than equals to fc. Fc is my critical frequency or cutoff frequency, whatever you say, and it is 0 beyond the cutoff frequency. And this is, I am taking the example of a low pass filter, and this general concept can be easily extended to other forms of filters. So, what should be the impulse response? So, this is typically a box filter, and a box in frequency is a sink in time and vice versa. So, if you see this, this is with some adjustments, this is a sink function is sin x by x. So, if you look at this function, this is my h t in the continuous time domain. So, what should be my response in the digital domain? Well, this is my response in the digital domain, and here what I see here in this case, this is here my analog frequency is non-limited, it is going from negative infinity to positive infinity, but my digital frequency is limited from minus pi to pi. So, it will have a gain of 1 from minus omega c to plus omega c, and from that omega c to pi range it will have a gain of 0, and this is the ideal filter. And its impulse response in the discrete time will be, so well this is the value, because this sink function will become 1 because of this limit, and so at n equals to 0 this is the factor which is omega c by pi, and this I have taken out just to make this a proper sinc function, and at n not equals to 0, this is my like gain or the response of the filter, which is omega c by pi and sinc of omega c n. So, this is the response of the ideal filter in the frequency domain, and in time domain this is the response. And here this is not limited to 16, I have just shown up to 16. Here also frequency is going up to infinity, and here n is going up to infinity, and of course up to minus infinity. Now, the first problem with this filter is that it has infinite length, but okay, IIR filters have infinite length, that is not a big deal. But the big deal is that this system is highly non-causal, because causal filters should not have any values below n equals to 0, because if I have something at n equals to minus 1, that means it is taking one future value of the input. So, this is not possible to realize in real life. So, what is the windowing method? So, we see that this ideal low pass filter h of n is non-causal. It is not only non-causal, it is highly non-causal, it is going fully up to negative infinity. So, it cannot be realized in practice for real time signal processing applications. So, what can we do? So, we can select a few samples by multiplying it with a window function. Now, typically if I say that I will only select this minus 8 to plus 8, that is this 17, 16 plus 1, 0th sample, 17 samples, and this will be my filter of order 17. Well, that is possible, and although this is non-causal, so this is the filter, this is of finite length. What we will do is we can put a shift of plus 8, so that this 8 becomes at 0. So, first of all I get a symmetric filter, which means it will be having linear phase response, and second is I will have a causal filter by shifting this to the positive side, that is introduce a large delay n naught, and in this case my delay will be 8 samples. And then after shifting this, everything beyond this window is set to 0. And this method, since I am multiplying this, I am selecting this, means I am multiplying these regions by 1 and rest as with zeros. So, this is I am multiplying it with a rectangular window, which is having a value of 1 in this region and rest are zeros. But what is the problem? This looks so good, but the resulting system is no longer having an ideal frequency response like the one which we desired. So, this is what I was talking about. So, you shift this and then take the window. So, basically what we are doing is, so we are multiplying the desired response. So, here just the window is shifted. So, basically I will shift the whole thing, whole signal, and that becomes your h of n, which is my desired response. This is my desired response, which is shifted and then multiplied with the window like this, like this. So, here if this comes to 0 index and this comes to your index whatever it says 17. So, it is symmetric and it is finite length. So, this is my final design. So, if I do this, so this is my actual response. So, this h of n is my actual response, h d of n is my desired response, or you can say the ideal response, which is the infinite non-causal response, and this w n is the rectangular window. This is w n is basically having 1 for this window range, that is 0 to your n naught, and this is after you set a delay to the signal, and it is 0 otherwise elsewhere. So, when I am doing this multiplication in the time domain, so it will become convolution in the frequency domain. So, this is a convolution. So, what is happening is that, so this was my desired response in the frequency domain, right, at omega c. and then I am multiplying with the window function. So, what is the, so if this is my window, what is the spectra of the window? The window is a box function. So, I will get the spectra, and this is the magnitude spectra, say. So, magnitude spectra will be a sink. So, sink is like this, but since this is magnitude, so everything will be plus. So, I get like this. Now, if I do a convolution of this with this, what will happen? We get something like this, where the ideal response is no more ideal, but this is a practical response. So, what is happening here is that, so instead of getting a sharp cutoff at omega c, we get a smooth cutoff, and this is called omega p, which is the passband representation, passband frequency, and this is the stop band frequency, and this is called my transition band. And so, for a good filter design, this transition band should be as low as possible. Similarly, so there are some ripples in the stop band, and there are some ripples in the pass band. So, this ripple, you can say this is plus minus delta 1. So, this is called the pass band ripple. So, this range is twice delta 1, and similarly this delta 2 is the stop band ripple. So, now if you see that this rectangular window is bringing this kind of response, which is not a very good response. So, can we do better? How can we do better? Maybe I reduce the transition band, or maybe I reduce the ripples in the pass band and stop band. So, based on that, there are different windows. So, the rectangular window which I have explained is easier to understand, but this may not be giving you the best response because of the sharp cutoff. Because of the sharp cutoff, you are getting that kind of sink response, which is making the actual response very poor. So, there are some modifications to this window, like the Hamming window, which is given by this equation. There is a Hanning window, which is also sometimes called the cosine window. Then there is a Bartlett window, which is like a triangular window. There is a Kaiser window. So, these window functions are developed, and there are some advantages of each window function against the others. So, this is basically the windowing method of designing your FIR filter. Similarly, you can design your FIR filter using least square or equiripple methods. So, equiripple as a method suggests that the energy in the ripples are distributed equally to get a better response. So, I will not cover the equiripple and least squares in this lecture, but this I just covered this one method, which is the windowing method, so that you know at least how to design this FIR filters using window method. So, you are highly recommended to read the least square and equiripple methods as well from any standard textbook. So, we will quickly now go to the IIR filter design. So, IIR filter design, here the catch is that in FIR filter we know exactly how many values of Hn we require, but in IIR we do not know, because there is infinite number of points of Hn. So, naturally it will be foolishness if I am trying to design all the infinite values of H of n, right. In the difference equation also, do we write infinitely many times for x of n? No. Like for example, take the accumulator as an example. So, it is accumulating everything from past. So, y of n is given by sum of your I from negative infinity to n x of I. So, if I represent this as an say FIR system directly, it is very difficult to get, right. But if I represent as yn minus yn minus 1 equals to x of n, right, because this I can just take out this x of n, and the remaining is up to n minus 1, which is my y of n minus 1. Like this step, if I write one more step, that yn is my, so I take this n and write x of n plus this becomes what? This becomes So, n minus 1 because I have taken n out, and this is x I, and what is this? This is y of n minus 1. So, this IIR way of writing this IIR way of writing this is a better representation, and that is why we get that numerator denominator part in the h of z. So, this process might be very difficult like the methods we discussed in the FIR case. So, what typically people do is, or how it is designed is, first the analog filter is designed HA of S, and then this analog filter is converted into a digital filter HZ using a mapping from S to Z, and based on the mapping there are different methods. So, why this is taken? Because analog filters have been widely used before the birth of digital filters. So, analog filter design topic is quite matured and well developed. So, you can very nicely design any analog filter based on the specification. And now, once you have designed the analog filter, you just need to convert this H of S into H of Z using some standard mapping. So, analog system or an analog filter can be described by this function n of s by h of s in the Laplace domain. So, h a of s is stable if its poles lie in the left half of the S plane. Now, if you want to design a stable IIR filter, so the analog filter's poles, if it is stable, then the filter's poles will be in the left half. So, in the digital domain also it will be stable if my j omega axis in the S plane it is mapped onto the unit circle, and the second is that the left half of the S plane, because these are the values where if the poles lie the system is stable, should be marked into inside of the unit circle. So, this is the condition for stability in the Z domain. So, what we will do is the first method is approximation of derivative. And in this case, so we will first approximate a derivative, that is dx by dt. How do we approximate this? So, this is x of n minus x of n minus 1, and this difference is accounted for how much duration? That is my sampling duration Ts. So, if I need to do this conversion, then what will I do is, so I have to map this. So, basically what is happening here? So, this is basically, if you see, this is 1 and this is a delay. So, delay is Z inverse, right. So, and this is the factor Ts. So, this S, because this is S into x of s in the Laplace domain. So, this S into x of s is basically mapped as, so this 1 minus Z inverse by Ts into H of Z. So, let us see for the second order differentiation. So, if I do the second order derivative, so I get this. So, first it will be x of n minus x of n minus 1 minus of x of n. So, this is what we are getting, x of n minus x of n minus 1 minus x of n minus 1 minus x of n minus 2 whole thing in bracket, right. And this will be T s square, this 0 will not be there, this is by mistake. So, by T s square. So, now what we get is basically, so here if you see that this is basically that this is 1 minus 2 Z inverse plus Z inverse square, if I transform into the Z domain. So, this is what I am getting. So, S square is mapped to 1 minus Z inverse by T s whole square. So, clearly S is mapped to 1 minus Z inverse by T s, S square is mapped to I can take the whole thing. So, similarly, if you see S to the power any value k will be mapped to, so this is by induction you can prove it, this. So, the approximation of derivative is nothing but this mapping, that this mapping. So, this is what we are getting. So, if you see, so this desirable property is there, that S left half of the S plane is mapped onto the unit circle and not only the unit circle, it is much less than the unit circle. This is a circle of half radius. So, this is a problem that only a very small area is utilized. So, you can only design low pass filters and band pass filters having relatively small resonant frequencies, because you are not utilizing the full stable region, you are only utilizing a very small portion. So, to solve that, another method is developed, which is called the impulse invariance method. So, here the objective is to design an IR filter which is having this impulse response h of n by sampling the analog version, which is h a of t. So, if I see the transfer function of the analog filter, so this is like a sum like this, and this C k you can get by the partial fraction thing. Now, this will be typically the poles, of course, because at these values of S our response will go to the infinity. So, if I take the inverse Laplace, so this I get, that is C k, which are the coefficients e power p k t, and if you are having confusion, just check the inverse Laplace table. So, if we sample this impulse response, because that we are supposed to do, a sampled version of the impulse response. So, we get h of n from this, which is h a of n t s for different values of n. Again, I will keep n from 0 to infinity, not negative infinity, to keep it causal, and then I get this basically, which is this, just plugging in at t, we are plugging in n t s, and this is basically now we got the h of n. So, there are say n poles, so we will go up to n, and then the next thing is that we will use the formula for Z transform. So, here this value of h n we will plug in this result to get this expression, and just arranging. So, I take out the C k outside, and this term is basically a GP series, infinite GP series. So, this can be evaluated to 1 by this thing, right, and this C k is the factor. So, technically where are the poles? So, poles are at e power p k t s. So, in general we can say that this is the mapping. So, the poles of the analog are mapped to the poles in the digital. So, at z equals to e power s t s we get the response. Now, there is a situation here is that, so in the continuous domain, if I have a frequency response like this h of f, or say capital omega, which is the analog CTFT, in the DTFT what we get? We get h of small omega, which is basically the replica, and this is periodic with period 2 pi. So, sampling makes replicas, periodic replicas of my spectra, right, and that is why these are like after one cycle, then this is repeated, this is repeated, this is repeated. So, if it is beyond this Nyquist, then there will be aliasing, and naturally you have to keep it in the low frequency region, that is half the sampling frequency. So, what happens here is that, so I can design only low pass filters or band pass filters. I cannot design high pass filters because of the spectrum analysis in the sampling process, because else if I design high pass filters, then they will merge and there will be aliasing. So, the final method of this course or this topic is bilinear transform, and here what we do is, here we will convert the analog to digital while preserving the frequency response characteristics. So, this is the transformation, that is 2 by T s 1 minus Z inverse by 1 plus Z inverse. So, here this is a conformal mapping that will transform the j omega axis onto the unit circle only once, unlike the impulse invariance where you are getting like this copies like this. Here the whole minus infinity to infinity will be mapped to the circle only once, and this will avoid aliasing of frequency components, and hence you can design high pass filters using this method. So, this is what I was talking about, and your stable causal poles will be inside the unit circle to make it stable causal poles in the Z domain. So, here what we will do is, instead of substituting a finite difference which we did for approximation of derivative, here we will integrate the derivative on the left side and approximate the integral using a numerical method which is the trapezoidal rule. So, say we have dy by dt equals to xt. So, if we do integration of this and we take one sample duration, that is n minus 1 Ts to n of Ts, and same we do for the right side. So, the left side we do the integration. So, dy will be y and the limits will be n minus 1 Ts to n Ts, and in the right side we will evaluate this integration using the trapezoidal rule. So, here we get y of n Ts. Now, for y of n Ts is basically y of n, and similarly y of n minus 1 Ts is y of n minus 1. And here the trapezoidal rule is basically, this is area under the curve, right. So, this is you are getting x of n Ts, which is x of n, plus at this x of n minus 1 Ts, which is x of n minus 1, this plus this by 2. So, this is the formula to calculate area in a trapezoid. So, by 2 into Ts. So, this is basically the trapezoid. So, we are doing this area. So, this is NTS and this is this is NTS and this is n minus 1 Ts. So, now this is what we got in the previous stage. So, if we take the Z transform of both sides, this is what we get from this, and here this is what we get. And now doing simplification. So, taking yz common, 1 minus z inverse, and this is taking xz common, this is what we get. And if we rearrange, we get 2 by Ts, 1 minus z inverse and 1 plus z inverse. So, this is what we get, and this is the thing which we got in the analog domain, because since xt was dy by dt. So, in the Laplace domain xs is s times ys. Now, if you compare these two, you get this mapping which we discussed in the beginning. So, this is basically our bilinear transform to map the S to Z. So, thank you so much, hope you have enjoyed. Thank you very much, have a nice day.